Another beautiful day, everybody. Hope you get to take advantage of the weather outside sometime today.
No, I work. Oh, you work Thursday?
I'm sorry to hear that.
I'm at work
No?
all night.
Oh, practice. Okay. So, even though it's not winter anymore, do you guys remember how dry it gets in winter? Does anybody get really dry and they have to use, like, lotion and stuff if your skin gets chapped? I have that issue sometimes with my hands. My hands get really dry. Anybody tell me what the leading cause of dry skin is?
Dry heat.
Nope. Good guess.
I know it's a joke.
Towels! That one's not bad. Oh, come on. Your standards are way too high. Because towels dry your skin off when you're wet.
Yeah, good to explain the joke. It's not a good one.
Oh.
Huh?
Anyway.
Yeah, boo!
So, how about the next one here? If you didn't like that one, you're probably not going to like this one. Why is it that the large cat got disqualified from the race? He was a cheetah. Ah, this is a tough crowd. Come on.
That was definitely better than the first.
Thank you, Sam.
You're better jokes.
Okay. So, one thing that is not a joke is our notes today. So, why don't you go ahead? You can start by writing this down. It should be pretty much review. We are going to transition from straight line motion into circular motion today. So my goal is to make your head spin a little bit. Is that better than the other one? Now, these equations should come as no surprise to you. The only difference is that instead of v being just regular velocity in terms of meters per second, I added this word tangential. And that's an important word, and it's something that we have to use to identify whether or not this is a velocity or an acceleration going in a straight line, or if it's going in a circle. We use a different word. And I'm going to put those on the board shortly. So before we do that, though, how many people in here have been on a merry-go-round?
I've been on one.
Okay, good.
They suck.
They suck?
Well, they're okay.
Wow, this class is just full of critics. So,
They suck.
So these merry-go-rounds, you got the horses on the outside and the horses on the inside. When you guys went on this, did you guys tend to pick the horses that are on the outside or the ones that are closer to the middle?
Outside.
Outside.
I just picked the coolest looking.
Yeah,
the coolest looking one.
Those of you who said the outside ones, why did you say that? Yes.
Felt like you were going faster.
Yeah. And you really are going faster if you're on an outside horse. I felt the same way. I'd always pick the outside horses to ride on because your tangential velocity is actually greater if you have a larger radius, if you're further from the center. Because, yeah, velocity is distance over time, but if you're moving in a circle, that distance is equal to the circumference, which is 2 pi r, and it would be that divided by time. So if you pick a horse further out, it has a larger radius, and you've got a bigger velocity. So that's absolutely true. Now, acceleration, of course, is a measurement of how quickly your velocity is changing. The main place I want to go with this, though, is the second type of velocity. And the second type of velocity is going to have to do with how many revolutions per second each of those merry-go-round horses are going through. So regardless of whether you pick a horse on the inside or the outside, you're still going around the same number of times in the end. So there's a different type of velocity we use for that. And that's called angular velocity, and it's abbreviated with this little curly W. It's a lowercase omega if you want to get specific about it.
Lowercase omega.
Yep. So we call that angular velocity. And we deal with this in terms of radians. So instead of being meters per second, it's radians per second. In other words, how far, around that circle are you going every second in terms of radians? And the equation is just going to be the velocity that you would calculate divided by whatever the radius is. On the same note, we have a new version of acceleration along those same lines, and that is lowercase Greek letter alpha,
Oh, it's like the Jesus fish.
also known as Jesus fish, and that is angular acceleration.
What if, like, this whole time Jesus was just a fish? No, like, all the stories
Yeah,
about
I got
him,
it.
but, like, he was just a fish.
He did say he would make us fishers of men. Then we've got radians.
Didn't make a big splash.
Very good.
Yes.
Radians per second squared would be the units here. Just like in regular straight line acceleration, it's meters per second squared. And as you can probably guess, the way you would find this value is by taking your straight line acceleration and dividing that by the radius. So again, the main thing here is if you're on a merry-go-round and you're looking to have a greater velocity or acceleration, you want to pick an outside horse because that radius matters. The bigger the radius, the larger those values are going to be. But if you're measuring angular velocity or angular acceleration, then your radius doesn't matter because you're covering the same number of radians that go in the circle in the same amount of time. It takes you the same amount of time to go around once, whether you're on a horse in the middle or on the outside. Yes?
You know what's crazy? Like, I really figured, like, all this out when I was, like, 5.
Yeah, isn't that neat? See, physics is something that you've been doing already from a very young age.
Outside just makes sense because you're like, whoop.
Yeah, exactly. Nobody wants to be in the exact middle where it's like you're going super slow. I suppose if you're in the very middle, you're just kind of going like this. But anyway,
Yeah, but sometimes they have cool designs in the middle.
I suppose.
You know what's cool about the middle is, like, if you're just not moving, you can just see everybody else in chaos, and you're just chilling there.
Thanks. I hear ya.
Sounds like-
Now, I just got done saying that radius doesn't matter for these, but here it is in the equation. The reason it's in the equation here is because it's assuming you've already calculated the actual velocity. So, if you're on an outside horse with a bigger radius, you'd have a larger velocity and a larger radius. If you've got a horse closer to the middle, you would have a smaller velocity because you've got a smaller radius. So smaller velocity, smaller radius, kind of like the Newton's second law thing, the ratios cancel. You'd get the same angular velocity and angular acceleration regardless. Questions on this? Okay. I think maybe we should have merry-go-round music playing for passing periods. How about that?
That'd drive me crazy. Yeah, and we have, like, scary clowns around, and, like, if you get caught by them, like, they take you away.
Wow, that took a dark turn.
No, it's not supposed to be dark. It's like,
We go from merry-go-rounds to scary clowns. Are you thinking about, like, It?
Hand in hand in scary movies, though. Like, if you hear it.
The movie It? Is that what you're talking about?
oh yeah, with Georgie and all that.
Oh, yeah.
Okay. So, we got to keep going with this circular motion here. And I'm just going to get rid of this real quick. I've actually never seen that movie.
I remember I was in 8th grade and I saw it, and I genuinely almost crapped myself.
It's kind of overrated.
Well, like
It
I
is
just
very
didn't
overrated.
expect 5 minutes in for some little 7-year-old's arm to get chopped off by an evil clown teeth. It's like, oh, 5 minutes in.
That part's the only scary part.
That's the only scary. Yeah, I remember it was like the first rated R scary movie I've ever been to in theaters, and it's like the first 5 minutes I see that, and I'm like,
Oh, I'm in for a long
this is gonna be great.
Watch out for those storm drains. So let's take a look at these
I wanna
things in
float
terms of
too.
motion. We talked about acceleration several times already. And in order to figure out the direction of acceleration, the main thing that I did was I took water that was in a cup, and in this case just a little water bottle. And if you remember, I moved in a certain direction, and then the water came out, obviously. So if I'm going to go this way towards the door,
Oh god.
the water comes out the back. And if you remember, whatever direction the water goes, the opposite direction is the direction of your acceleration and your force. Now, of course, that means my acceleration and force was going this way when I was going in a straight line. What do you suppose happens if I would take this and I would go around real quick like that? Who's going to get wet, you or me?
Us.
You guys are, because the water's going to head out in that direction. Now, what does that mean in terms of the direction of the force and acceleration when you're moving in a circle then? If the water goes out to you.
Oh, it's toward you.
Yeah, it's going towards the middle. Anytime you have circular motion, not only is the force going towards the middle of that circle, but the acceleration is as well. And we'll talk more about that as we go forward with this. I'll show you a quick example. Where'd my world go? There it is.
God be like.
So stupid.
That was funny. All right. Now, let's say you've got the world on a string like I do here. And you're swinging it over your head like this. Now, if this is occurring, we already said that the direction of force and acceleration is pointed to the middle of the circle. Now, I want you to consider what direction do you suppose this world would go if the string would snap right here.
Yeah.
So would it go straight across like this, or would it kind of angle a little bit?
I don't know. Straight.
It's an interesting question, isn't it? You don't have to put this in your notes, but I just want to draw it out here. So if the string is coming like this, here's the world that we're swinging around, and if it's heading in, if it's heading in this direction, and the string snaps in that location,
Oh, it's
remember, in the same way that once you let something go, it retains nothing of the force of your hand. It just moves on its own. Same thing is true here. Even though it's moving in a circle, as soon as that string snaps,
just gonna go forward, right?
it's just going to go forward. It's not going to retain any memory of the curvature that it's been undergoing this whole time. It's just going to go tangentially in a straight line.
Is
Yes.
that why when like people do discus for track and they go in like a circle and then they throw it, it goes straight?
Yes.
It's like exactly.
Yep. So if you're, doing discus and you want this thing to go straight in that direction, you want to release it right here when it's actually moving in that direction. Yep. Okay. Now, if I continue to do this, the tension remains the same in the string the whole time, as long as I keep swinging it the same amount. But what happens if I change things up a little bit?
Oh God, no. I'm bad at change.
And now we are going to the side. So, what do you think? Does the tension in the string change or stay the same?
It changes
Sure does. Do you suppose it's more
more.
tensiony at the bottom, or is it more tensiony at the top?
I'd say more at the
Bottom.
top, right?
Bottom.
At the bottom, yes.
Yeah, at the bottom.
Because, like, if I slow it down, it's going to get slack a little bit when it's near the top. And it
It's
gets
gonna
tight
drop.
again when it gets to the bottom. And that's something we're going to take an even closer look at in just a little while here. But there are a lot of forces at work when something is moving in a circle. Anybody know what we essentially call a circular force? It starts with the letter C.
Circumference.
We're going to see how long it takes. I know you've heard this word before. So in the same way that when an object moves in a straight line, force is equal to mass times acceleration, same thing is true when you're moving in a circle. But there's something that these C's stand for. Yes? Yes, centripetal. Centripetal force is a force that's present anytime something's moving in a circle. Now, this is a huge point here, okay? So make sure you're listening up. This centripetal force is not a new force. Might be a new word for us, but it's not a new force. It is simply the net force that causes the object to move in a circle. So when I calculate this value, it's not something that's just a brand new number. It's always made up of things that we've already dealt with. So for instance, if I'm swinging the world like this, and it's going round and around and around, it has centripetal force because it's moving in a circle. At this point, that centripetal force is going to be made up, actually, let's say when it's on the top. That centripetal force is going to include two things. It's going to include the tension from the string, because without the tension in the string, it's not going to be moving in a circle. And it's going to include gravity, because without gravity, it would be moving differently as well. So in this case, when this is up here, the tension force is down, gravity is down. So what that would mean is that my centripetal force would be gravity plus tension force. So your centripetal force is not a new force. It's just whatever's acting that's making the thing move the way it's moving in a circle. Does that make a little bit of sense? Okay.
Without it, like it just, doesn't make it a circle.
Yeah. So that's centripetal force. If you need to write down centripetal, you're welcome to. The equations for this are in the force box on your formula sheet, and they are the right two columns. So you can see FC equals MAC, and you've got AC equals V squared over R. You've also got your angular velocity, angular acceleration terms, and a few others that we'll be dealing with in a little while. But yeah, so centripetal force is equal to mass times acceleration. Just think of this as your net circular force. In the same way that if something was moving in a straight line and it had an applied force this way and friction this way, the net force would be applied force minus friction. So centripetal force usually includes at least one, but usually two forces that are causing it to swirl around in a circle in the way that it is. Okay. That's complicated enough for now. Let's get into something a little bit more easy. So centripetal acceleration, and this is on your formula sheet, is going to be equal to V squared over R. So if you can actually measure your velocity,
I can't measure.
you divide that by radius, and that gets you your centripetal acceleration. And the units on this are the same thing as regular acceleration, meters per second squared. And that's that. All right. Did I miss anything? Hey, no, I think we're good to go. The only extra thing I'll mention before we start using this with some numbers is, has anybody heard the word centrifugal before?
Yes.
Okay.
I've heard all these words, I just don't know what they mean.
That's fine. That's why you're here. So centripetal force is the force that's always, it's like your net circular force, and it's always pointing to the middle of the circle that you're going around and around in.
Hand is?
Yeah, they'd be pointing to my hand right there, yep. Because it's always pointing to the middle of the circle. Centrifugal force,
Is the outside of it?
Yeah, the centrifugal force is actually, it's the direction you feel pushed. So if you were on this thing, going around in a circle, you'd feel pushed out. Just like if you're going around a turn, you feel like you're pushed to the outside of the circle. That would be considered centrifugal force. We don't deal with that in terms of numbers, but that is the force that you're feeling when you do that. How many of you guys have been to Six Flags and you've been on the thing that goes around super fast and you get pushed against the wall like this really
Those
hard?
are really fun.
Aren't they? Yeah. So what you're feeling is you're feeling the centrifugal force that's pushing you outwards, to the back and keeping you against the wall. But of course the wall is there to keep you from falling through. And it's providing kind of like a normal force in this direction, towards the middle of the circle. And that's what your centripetal force would be. So they're very related. The one that we're really going to be talking about most often is the centripetal force, but I just wanted to mention that so that you really know it is a thing. So yeah, let's go ahead and do an example or two. How many of you guys like to go on swings, either now or when you were much younger?
I did this weekend.
Nice. Unfortunately, I have some bad news for some of you. As some of you get older, you will get motion sickness from getting on swings like I do now, even though I loved being on swings when I was a kid. Even so, we're going to use examples that include a little person, a kid, on a swing like this. So go ahead and draw this as best you can. Make sure he or she is smiling.
That's probably like top 10 best TV shows.
I don't even know if it's from.
What?
Where's it from?
Regular show.
No.
Another really good TV show.
Yeah, no.
Regular show that's anything but regular?
I've watched all the regular shows.
Oh yeah, then how do you not know Hello Governor?
I just don't remember the quotes and stuff. So it's been a very long time since regular shows been on.
Well, there's a thing called seeing it in other places. There's a part of it. I'm just not going to get into it.
You sent me a video of top 10 muscle man moments. Middle of class.
Yeah, because I thought you might want to see the top 10 best muscle man moments.
Okay, so let's keep going with this swing example. Just kind of curious, what kind of stuff, when you guys were on swings, did you guys just go back and forth, or did you like to jump off and all stuff?
Here for that.
No? Okay. How many people like to jump off?
I like to sit in the
Nobody.
middle and then swing around until it tied the chain up and then just unspin myself.
You can do that.
That's always fun.
Puke.
My brother and I always like to do all sorts of things. From jumping as high as we could off the swings to, I had a thing where I would call it like a moonwalk, because like you would jump off right down here when you're moving really fast, and if you took one step, like your next step would be like 15 feet further. So it was really fun. The other thing that we did is we'd go real high and then we'd do the backflip thing where you hang on to the chains and then you backflip off. We thought we were pretty cool.
That's kind of insane. That's like X Games.
What?
Yeah, it's watch enough Ninja Turtles and you do stuff like that.
Oh my god.
Okay. So here's our example. This little guy is on a swing. He's going down, going up like that. The swing radius is 2 meters. He's traveling at 8 meters per second, which roughly corresponds to about 16 miles an hour. And he weighs 50 kilograms. So let's do a couple simple calculations before we dive into the more complicated stuff. Let's calculate this guy's angular acceleration. Well, angular acceleration is equal to v squared over r, and we just so happen to have both of those numbers. Velocity is 8. Radius is 2. So 8 squared is 64. Divided by 2 is 32, I believe.
Yes, sir.
Cool.
No.
So there's his angular acceleration. And again, that equation is on your formula sheet. Questions on this one? Oh, good. Well, let's calculate his centripetal force. So the centripetal force is going to be mass times centripetal acceleration. We know the mass is 50. We know the centripetal acceleration is 32. So we multiply those together. And I'm not like my wife. She could probably do that in her head in no time. I got to get it calculated. What'd you say it was? 1600? That sounds about right.
Is your wife super smart?
Yes, she is.
What does she do?
She's a piano teacher / musician for church / chiropractic technician / opera singer.
Wow, you must love your life.
Pretty fun. I love her. And indeed, that is 1600 newtons right there. But yeah, like, if we go out to eat, she's the one that calculates the tip. And she does not need a calculator. And she can get it down to the cent.
Wait.
And it's like, I couldn't do that in a million years. In my head. So yeah.
Okay. So, like, okay.
Did you just
Do you
pull
tip-
out the physicist
Do
card?
you tip, like, the exact
No,
amount
just-
for, like,
I'm
for,
humble.
the percentage?
What's that?
Do you tip the exact amount for the percentage?
Well, it depends. Usually, we don't usually go below 20, but if they're really good, we might go a bit higher.
No, but I mean, like, say you tip 20%, right? But, like, 20% is, like, $5.69. Like, are you going to tip exactly $5.69? Or are you gonna
No, we usually round up.
Okay.
Yep.
Yeah, because my dad, when he used to teach math, would always say, like, if you go on a date and you, like, bring out your calculator and the exact amount and, like, get out the code and everything.
Although, if she's like a math nerd, that could be like, there you go.
Wow.
All right. So again, when I say centripetal force, I am not talking about a brand new force here that's equal to 1600 newtons. This is your net circular force. In this case, it would be the combination of the tension of the string and the gravity down, because those two things are what cause this little kid to go back and forth in the fashion that he's going. Now, on to some stuff that's a little bit more complicated, but we're going to use the same picture. Who's ready for this?
No!
Oh, no.
No!
You don't have a choice. So, here we go. We're going to... When you're on the bottom of the swing, and you're going back and forth like that, when you're at the exact bottom, do you feel heavier or lighter than normal?
At the bottom?
Yes. Heavier, absolutely. So let's try and figure out how heavy this little guy is going to feel when he reaches the bottom of the swing there. So- That's one of the reasons. It has more to do with your brain and equilibrium stuff. But in terms of this example, we know his mass, so we can use that to figure out how heavy he'd normally feel. But what do we have to calculate if we want to find out how heavy he actually feels under these particular conditions? What force is that? Help me out. Someone's got to remember this. What type of force corresponds to how heavy you feel? Normal force. Thank you. So we want to calculate normal force for this guy. Now, in terms of the different forces acting on him, we've got normal force up. It would be the same thing as tension force in this case. They'd be the same number. But yeah, the seat is providing him with a normal force up, and there's gravity down. So, in our force equation, those two things are going to go in opposite directions. That's why we have the subtraction there. And we're setting those two things equal to ma, but because we're moving in a circle, this a is centripetal acceleration. So we put the little subscript there. So if we want to find out how heavy he feels, we just got to isolate the normal force. So we move gravity to the other side and see what shakes out.
Sure.
That's 1600, right?
Yep, we ran this calculation before, and that was 1600. Michael, did you do that in your head, or did you have the calculator?
Calculator.
Okay, I would have believed it that you would be able to do it in your head. So force of gravity is just mass times 9.8. So 50 times 9.8. What do we got for that?
4.
Looks like we got 490.
Oh, you got it right.
So when we add these numbers together, we're going to get
Oh my god.
2,090 newtons. Wow.
That's a lot of newtons.
Yeah, this kid feels very, very heavy. Because,
As heavy as sand.
remember, as heavy as he regularly feels is his force of gravity, which is 490. So under these conditions, he's 4 times his weight. He's undergoing about 4 Gs,
You've been eating
which is, this is a
Jeez.
powerful swing here.
You've been eating too many fig newtons.
Yes, he has. He's a little fatty. Okay, questions on this? Okay, let's go to the next example then.
Too many fig newtons.
Hey, dude, don't even fatty.
I know.
Has anybody gone so far on your swing set to try and go as high as you possibly can, maybe even going all the way around?
Yeah,
I'm trying.
Okay, did it work?
maybe Keegan in his earlier days would have been able to go
Hey,
with
man.
that.
It didn't work for me. And now this little kid's going to give it a try. So go ahead and draw that in your notes.
Some fat shit today.
Postage. Postage. Have you ever seen that picture, Mr. Hathaway?
Which one?
That the one where I was a big boy and it was me at Bucks Camp.
And it's just the caption under it. Post.
Oh, let me pull it up real quick. Yeah, I got you. Yeah. Oh, you're gonna die. You're gonna
It's my
die.
favorite picture.
It's so
It's one of the
funny,
best
dude.
pictures I've ever seen or taken.
Let me know when you have it.
Okay.
My caption there.
So, this new scenario, this little guy is now upside down. He's gotten to the point where he has gone all the way around and he's at that halfway point on the top. Now, depending on how fast he's going, one of two things is going to happen. He could be going fast enough that he'll be just fine. Like the world right here. And just like on roller coasters at Great America, you got it up?
You want to see it?
Yeah, bring it up quick.
Oh, you're gonna lie. Postage.
Nice.
Yeah, it's pretty good.
Let me see that. Let me see that.
So on roller coasters at Great America, if you're going fast enough around a loop, you actually don't need like a chest harness or a lap harness at all. You'd remain in your seat if you're going fast enough. So the same thing is hopefully true for this guy. We're going to find out. If he's going fast enough, he'll have no issues. But if he's going a little bit too slow, then he's going to fall right off of that seat. And there is a particular velocity where that's going to occur. We want to figure out what that velocity is, and then try and figure out if 4 is bigger or smaller than that, and then we'll be able to see what this little guy's ultimate fate is going to be.
Why are you smiling like that?
Now, here's the thing. If you go around fast enough, you're going to feel a certain weight when you're up at this point. You're going to feel less heavy up here than when you're at the bottom like before. But if you're going fast enough, you'll still feel like you weigh something. So what we really want to do in order to find out what this minimum velocity is for him to actually make it all the way around, what we need to do is think about what's going on with the forces here. We've got gravity going down, and we've got normal force going down, because the normal force would be pushing him towards the center of the circle, same direction as the tension force. So we've got normal force plus force of gravity, because they're heading in the same direction, and that equals ma. Any questions on where this equation's coming from?
Mississippi.
No, that makes sense.
Okay, good. So, if we're thinking about the minimum velocity he needs to just barely make it all the way around, if he's just barely staying in that seat, what is his normal force going to be?
Not that high, right?
Oh, I thought you actually said it. I thought you said nada. It's going to be 0.
Oh, nada, yeah.
Because if you're at that velocity where you're just barely making it around without falling out, you're going to feel weightless. So all we do to find out what velocity that is we set the normal force equal to nothing. So then we say force of gravity equals MAC. So let's see here. Force of gravity, 50 times 9.8. What was that? 490, I think?
Yeah.
Okay. So force of gravity is 490, and that's equal to his mass, which is 50 times centripetal acceleration. So that's v squared over r. We know the radius is 2, so we got to solve for velocity. Once we solve for this velocity, we'll know the minimum speed necessary for this little guy to remain in his seat as he goes all the way around that swing set. So, let's do this then. 50 divided by 2 is equal to 25. So if we want to get this v squared by itself, we got to take that 25, and we have to put it underneath here. So 490 divided by 25 is equal to 19.6. And that's equal to v squared. In order to get rid of that square, we erase it, but then we got to square root the other side. And that gives us a velocity of 4.43. So what does this mean for little Johnny on the swing there?
He's not going to have a good time.
No, he's not. He's not quite going fast enough to make it all the way around. So he would fall out of his seat somewhere over here. But I'm sure he's got several mattresses and pillows underneath, so he'll be just fine. And he's young and durable, I'm sure. Questions on this?
Like a roly-poly.
Like a ragdoll.
Okay.
So we should just ragdoll him.
So this is the same kind of work that you'll have to be doing on your homework. I'm going to hand it out to you right now, but we'll have all of class tomorrow to work on it. Any last questions? Okay.